let's go to our Q&A session. And yeah, I'm GEM model. I mean, this is one of the big ones. So I'm really excited to have you here. So again, that's Option Y on Mac or Alt Y on Windows to raise your hand. And let me see, I'm going to allow everybody to unmute themselves, but go ahead and please raise your hand if you have a question. And Mr. Vallone, well, welcome back, sir.
Thomas Vallone.
Or
Yes.
Dr. Vallone, my apologies.
Dr. Vallone.
Tom, you're muted.
All right.
Okay.
Hopefully you can hear me.
Yeah.
Yeah, I can.
I've been waiting years to hear this lecture. Every time.
Oh, no kidding. I'm very honored that you would say that.
and I almost got you as a speaker to actually give this lecture at our conference on future energy years ago.
Oh my God. Okay.
Work out. So it's okay. I'm finally.
It all works out.
Rewarded by sitting here and.
I'll appear at your next one. I'll be happy to zoom into your next one.
Yes, poach our speakers, please. Tom, poach our speakers. Okay. If you would like a list, I can provide you with a lengthy one, sir.
Sounds good. Well, I have some questions, and
sure.
The first one is, when you started off, I was actually thinking that you're going to include Puthoff's famous.
Yeah, and I'm sorry, I glossed over that. Puthoff, Hal Puthoff is a friend of mine, and he, I think he made valuable contributions to the Sakharov model of ZPF.
Right. Yeah.
And of course, he's he's always been on the front lines of, let us call it phenomenology.
Well, he uses the stochastic approach to.
Yes, he does.
And that's really exciting to see how simplified those papers of his, and also, the two other associates that were.
No, I salute Hal Puthoff for his contributions to this with his SED theory. I'm sorry. I basically, this is a kind of a talk given to mainstream physicists who don't like SED, so I put in QED instead.
There you go. Well, the basic question I have about that is, how are the two related? Because obviously his approach is quite different. He's including the ZPF, and then he does the E cross B effect, and it's like the low frequencies, I believe, and then inertia. A separate paper in PhysRev is the higher frequencies of the universe.
I've looked carefully at his theories, and I find that my theory is basically kind of a limit of his theory, except the hydrogen and proton masses don't enter into his theory.
Ah, interesting. Okay.
It's the second postulate, the deployment of the hydrogenic system, the proton and electron. That's one of the keys, and he didn't go there.
I see.
And judging by the reaction of some mainstream physicists at conferences, I can understand why. I gave a paper at the Division of Particles and Fields. They gave me a poster, and I was terrified, deeply terrified that I was going to be ignored and put off in some far corner of the auditorium, drinking my beer and minding my my poster session with nobody coming by. But to my delight, I was met by a mob with pitchforks and torches instead. I got attention. And some of the reactions of people were really, really classic. I'm sure you guys have all endured this. There's there's schools of thought in physics, and we're smoking in the boys' room. I'm sorry. Or at my high school, there was an area outside the gym where everyone would go and smoke and do other things. And that is kind of that's our community. That's our community.
That's us. Yeah.
Okay, one other question real quick.
Sure, I'm sorry, Tom.
Any gravity, but all of this should lead to some new breakthrough in a propulsion system, or how to use gravity to produce the opposite effect, or, you know, come
That's
on.
a very, very interesting point.
You're talking to a progressive audience here. We can let you loose.
Well,
No pitchforks.
there's no torches and pitchforks. We do have a patent lawyer, though. I'm sorry,
Oh,
you know, I was discouraged from talking about that in this introductory talk by my bosses.
But SpaceX has you on a retainer, right?
Yes.
Oh, good. I'm glad.
If
And
I
we
could
intend to go to
actually,
Mars.
if I could jump in really quick, John, what I would like to ask is how you're feeling because of COVID.
Oh, I'm feeling great.
Okay, good.
But I was there 4 months in the hospital. Well, anyway, I looked like I was gone for a little while, and I know 2 people who have died from COVID, Delta. So it's quite a formidable experience. And anyway, I'd rather not dwell on that.
Yes.
Just say that God sent me back from the pearly gates after knocking on the door there, and St. Peter said, "Go back. You're not done yet."
Yep, we feel the same way.
Well, all of us are here for a purpose, you guys. Let's finish this thing.
Yeah.
Have Jetsons flying cars.
Okay. So
among other things.
Well, Tom,
I'm sorry, I keep turning off my phone and it keeps ringing. I don't understand it.
Yeah. Tom, thank you, sir. And I would like to have Mr. Malone back as well. Oops. And let me see. And now we have a bunch of new people joining the conference. Let me go to Michael next. Michael, go for it, sir.
Hello again. So
yes, Michael.
Thanks so much for doing this, John.
Oh, you're very welcome.
Yeah.
So thanks, my father and Edward Teller.
Yeah. So I noticed the well, first off, the plasma, like the pointing drift thing, that's really cool. I wasn't aware of that in plasma physics.
Yeah. Look it up under particle drifts, like on Wikipedia or any E cross B drift. Just do a Google on it.
It reminded me.
It's a interesting secret that's not a secret. It's an open secret. It's very, very important in confining plasmas.
So it reminded me a lot of. I mean, you said Hal's a friend of yours. Have you seen Have you seen Todd Desiato's work? Actually, the previous speaker was working with Todd.
No, I'm sorry, I'm not aware of his work.
So another polarizable vacuum model,
sure.
But he derived something that seems extremely similar to the pointing drift concept that you had.
Yes.
Yeah, using so I guess, is your model fully compatible with the polarizable vacuum model, or does it differ in some ways, I guess?
Well, the polarizable vacuum model, is really one way of thinking about the ZPF. But I'm not really an expert on it. Hal and I basically would share ideas, and then we'd both go our separate ways.
I see.
He said, "That's interesting, John." He also liked my science fiction novel. So it's Morningstar Past, The Collapse of the UFO Cover-Up. I wrote it under a pen name. He called it The War and Peace of UFO Fiction. So anyway, cool. So Hal's a great guy, and I hope he's very well, and I believe he is, right?
I think so.
I think he's working up in Las Vegas now.
No idea. Not from my perspective.
Okay, pardon me.
So then I had one more thing. So in that derivation of this pointing drift you were talking about, he used the Lorentz gauge to describe the vacuum flux or the vacuum noise as magnetic flux. And then he used that magnetic flux to define this drift term because it's an extremely strong magnetic flux relative to the electric term.
That's right, and that's what I find, that the Planck length is dominated by magnetism.
Yeah, so I was curious though if you could equivalently, is there an equivalent for of the Poynting drift where you have an E squared term and a small b term? Because if you could, I think symmetrically you could choose something more like the Coulomb. I don't know if the Coulomb gauge is the right one, but if you pick your gauge that you're fixing, and then you have electric flux instead of magnetic flux in the vacuum, then you should be able to do it equivalently the other way, unless I'm missing something. It should be symmetric.
No, well, you.
Or why isn't it?
I remember looking at that problem. Basically, the way it's set up, it looks like that would allow faster than light speeds for the particles.
Well, that's the hope, right?
Well, yeah, that may be the front door. We're looking for the back door on this problem right now. You know, it's a very interesting limit. When I saw that it basically gave answers greater than C, and blame me for being conventional, I just thought, well, why don't I just concentrate on the limit of E over B less than 1 and leave it at that.
I would, perhaps we can do we can do an email later. Jeremy, Jeremy get me in touch with you.
Sure.
But yeah, there's definitely something there to look at. I mean, just imagine why does the charged particle, why do you see the charge once it's entered a black hole? Well, because it emits that charge since whenever that particle was created. So you have the whole,
that is an interesting point.
The whole time cone is full of that field, and you can think of it as an electromagnetic wave of zero frequency.
Yes.
Therefore, it takes zero energy to propagate that wave, in a sense. So that is faster than light because, well, it appears faster than light because the signal was emitted whenever in the past it needed to be emitted in order to be observed by the observer. So that's
a very interesting physical point. I hadn't thought of that.
Yes,
it does suggest
that, back and then forward again.
Yeah,
it's kind of like a Wheeler-Feynman absorber theory. But,
oh, you mean Wheeler-Feynman?
I think so. Yeah.
Yeah. That the future is talking to the past and vice versa.
Yeah. Well, we'll chat about it more later.
Yeah, we'll chat about that more.
There's other people.
That's a whole other subject.
Yeah, there's a lot of cool stuff going on there.
Okay.
All right. Nice talking to you.
Well,
great. Michael, thank you.
Michael, thank you, sir.
Thank you, Tom, for also your questions.
Okay, so let me Mr. Storti, do you have a question? Would you like to go next?
Yeah, right. So you can hear me now?
Yeah.
All good. Okay, on one of the slides there, you showed the Planck relationships for mass and etc. Right? However, if one derives actually from first principles derives those Planck relationships using Buckingham pi theory, what you get in the front of it, in front of each one of those terms, you get a K value, and K is your experimental relationship function. So it can be a single number or it can be a relationship, right? And the whole of thermodynamics is based upon Buckingham pi theory. So the whole of thermodynamics, right? So it's been around for a long time.
This is black hole thermodynamics.
No, just regular garden variety refrigerator.
Boltzmann constant.
Sorry?
The Boltzmann's constant?
the thermodynamics of that, yes, but no, it's not that K, right? So if you actually execute the procedure formally, you get the relationship that you've gotten written there, but you get a K out the front of it. Same with E equals mc squared. If you derive E equals mc squared from first principles using Buckingham pi theory, what you'd actually get is K. So E equals K mc squared, right? Where K
Interesting.
is right? So if you include that experimental constant or function in as your starting point, so if you include it in those equations that you've used as your starting point, you've got an unknown K, and that value of K in the case of mc squared is assumed K equals 1. So every time you see mc squared, that's actually a specific solution to a general solution, right? And the same with every time that you use Planck charge, mass, etc. That's K equals 1. It's an assumed solution. So if you no longer assume K equals 1, so that you get exactly the relationships that you've got, and you generalize that solution, you leave the K's in there. So my question is, would that affect your procedure, the execution of your procedure and your end result?
Well, it would certainly add a new parameter, and the numbers fall out pretty close. So I basically declared victory at getting a few percent.
The reason
and close, and so I'm not familiar with the Buckingham pi theory, but I will become familiar with it, and I'll have more comments on that later.
You can find it in kind of any fluid or thermodynamics textbook, right? But the reason I brought that up is because my second question is, do you think, and I don't mean this in any negative way, but don't you think that drawing upon a fifth dimension, via Kaluza-Klein, it's really like convenient? I mean, it's when something falls over that.
Oh dear, are you calling it ad hoc?
Well, no.
In my opinion, by the way, all of physics is ad hoc.
You're probably right. We
invented physics because we were trying to solve other problems.
Yeah, you're probably right.
Well, I like Kaluza-Klein theory because it's derivable from this variational principle, the Hilbert action principle.
Yeah.
But I love action principles.
Okay.
It's just a personal preference.
Yeah, fair enough. And look, just one comment I might make regarding your COVID. Look, I spent all of 2021 in hospital. I've got blood cancer, so I'm.
Oh my goodness, sir, you look very healthy.
Oh, thank you. I've just come out of my second bone marrow transplant, and so I know. I'm very mindful of how dangerous COVID is, especially with me. So, yeah, listening to your story, sir, I can absolutely empathise with you totally.
Well, thank you, Riccardo, and I'll be praying for your good health.
Oh, thanks,
Continued good health. You look very healthy. You look well.
Oh, thank you. Yeah, healthy is
another way of saying
fat.
Yeah. Well, guys, if it's okay. And Riccardo, I want to say thank you. And let me go to Michael Boyd next, sir.
Mike.
Hey, John, I got a question.
Sure.
So I'm curious, are you familiar with semiconductor physics?
Not really.
I
like to roast things. I like to take semiconductors and turn them into a gas and then keep heating them until they turn into a plasma. Then I understand them.
How about the concept of band gap?
I knew you were going to say band gap. You're so busted.
That is a very interesting concept. Yes, there is. I Yeah, but please continue.
So I had this discussion with Hal Puthoff about 0-point field, and basically my hypothesis is it's a anti-gravitational field. It's as opposed to a 0-point field.
Well, in a sense,
And
that
that's based
falls out of
on,
my theory because the presence of the ZPF creates anti-gravity, so to speak, that cancels the mass of the ZPF.
so I have these, I have like 4 patents on a thing called gravitomagnetism or gravitomagnetic induction,
Yes.
which I discovered in the late 90s, working on hard disk drive assemblies, where
Oh,
I
interesting.
created little nano bumps and nano pits on a disk and used the magnetic sensor that uses your head, and your head, read head, is a thing called a giant magnetoresistor. And I discovered that the presence of matter moving created a pull force that I could measure. And
it's interesting.
with a mechanical sensor called a piezoelectric sensor. It's a type of head they use to look for bumps on the disks when they're manufacturing disk drives. And I also discovered that the little nano pits produced a push force.
Push force.
And so I basically was looking at Hal Puthoff's research on this and his theory that there's a like expanded space-time and like when you're basically that space-time's not constant. It depends on where you are. And so like if you're closer to a star, then space-time's different than if you're like out in outer space, for example.
Oh, well,
Right.
I think that's just that's a way of enunciating general relativity. Yes.
So in matter physics or solid state physics, we talk a lot about band gaps and
yes,
and valence bands and conduction band electrons and
yes,
bonding electrons and non-binding electrons, that kind of stuff. So band gap's real important. So I asked Hal, what about the 0-point field? Do you think the vacuum has a band gap? And his answer was no, which surprised me. I felt surprised when he said that, because I think
he's a man of firm opinions.
So I'm curious how you feel about it. Do you feel that the vacuum has a band gap like matter does?
Well, I mean, certainly
something else.
The Planck scale ZPF doesn't interfere with anything that it's not directly observable, at least.
Well, when you
I thought if it was observable,
when you use the term Planck scale, when you use the term Planck scale, and to use the word observable, I get a little, I feel a little cognitive dissonance, because think about the Planck time and Planck length are so tiny that how would we ever measure anything at that scale?
Well, the ZPF energy density, if there wasn't some kind of decoupling between that and the mesoscale that we live at, we wouldn't be having this conversation. If we could observe the Planck turbulence, we wouldn't exist because.
Well, I would argue that except for the Planck mass, we can't, none of it is observable. But the Planck mass, if you look at it, it's like 22 micrograms. It's pretty big.
It is.
It's pretty big. And all the nano bumps I fabricated in my experiment were all much lower than the Planck mass. So I would argue that the Planck mass is the key metric. especially when we're
Interesting.
talking about gravity. Because
Interesting.
gravity is a property of mass, or the absence thereof, is what I
Yeah.
mean.
It's you raised some very interesting points. I'm afraid I can't really answer those questions, but they are very interesting ones.
Okay, thank you for your answer. I appreciate it, and keep it in mind.
Thank you.
And
Thank you, Michael, for your questions.
And I would appreciate it.
I'm going to look into Buckingham pi theory because, as I pointed out for Riccardo's talk, the expansion of the universe in his model resembles, a shock wave from a detonation of high explosive, and it goes as fast as it wants until it finally slows down and becomes the sound speed and
just
low
on
amplitudes.
that,
And so
would
that
you
kind of physical, there are all sorts of physical analogies I think we can make, and also from experiments we perform in
I was just
our
going to say,
everyday life, that everyday
would you
physics.
would you put your email address in the chat, please, so that I would like to share some of my data with you so you can see it
Okay,
for
very
yourself.
good. I will certainly do
Okay.
that. Yes.
Well,
Okay, thank you.
And Michael, thank you. Let me go to Detlef Hoyer next.
Yes,
Who's
hello,
been patiently
thank you.
waiting. And thank you for waiting patiently, sir.
You hear me? Do you hear
Yes,
me?
Yes.
yes, I can hear you.
Okay. Yes, I have a question regarding the E cross B drift.
Yes.
There was a slide with a capacitor with two plates
Yes.
charged and particles moving between.
And the magnetic field was coming out of
Yes.
the page
Yes.
at right angles to the electric field.
Mm-hmm. And could you explain how the
E cross B
drift acts on particles with different mass and charge, like proton, electron, and air?
Yes, you can derive it quite simply, not worrying about covariance or relativity or anything right now, just everyday physics. You take the Lorentz force and you equate it to be zero for a charged particle. So it is a condition of it's a drift, it's a constant speed, of course, unless it varies with space-time. And so you can look for V using vector identities such that the magnetic force and the electric force on the charged particle are balanced. And this gives you the E cross B drift velocity.
Is there a kind of friction which causes?
It's almost like a kind of friction. The particles.
So there is no acceleration.
There is a momentary acceleration when the particle first starts to move under, let's say, if you put the particle in there stationary, it would start to move in response to the electric field and be unaffected by the magnetic field because its velocity was so low. But then as the V cross B force builds up, it starts fighting against the electric force. And so what's interesting is the E cross B drift field velocity is a velocity where the charged particle effectively decouples from the crossed electric and magnetic fields.
I thought about the analog of a falling man from a plane.
Yes.
He accelerates until he gets about 180 kilometers per hour.
Yes,
and then
that is a good analogy.
Okay. Okay.
And I'm very fond of physical analogies because yes. Anyway,
yes,
it is really kind of a terminal velocity.
Yes, you talked about inspiration by Teller.
Yes.
A good inspiration gives you a good basis for good conclusions.
Well, when I heard him give a talk
to
on
work.
it, I thought, well, it is a good problem to work. So other people had said, oh, Einstein's quest for a unified field, it's a dead end. Don't waste your time with it. And but then Edward Teller gave a lecture on it where he had taken a running charge at it, and then confessed that he got nowhere. And he basically threw the problem down to us students. And I thought, okay, this is a serious problem of physics still. It's not a dead end. It's not a nonsense question like what lies north of the North Pole or something. And physics, as we all know, is a little bit like Hollywood. It's subject to fashions. And so thank you, Detlef, for your questions. Do you have any other questions?
No, thank you for your answer. Thank you.
Are you from Germany, by the way?
Yes.
Oh, very good. Very good. I visited
it's
Germany
late.
twice, and I was very, very proud to do
already
that.
Sunday here.
Yes. Well,
My family, I'll tell you, my family got kicked out of Germany in the 1700s because we would not take off our hats for somebody. And that's all it took in old Berlin to get, even with the name Brandenburg, to get kicked out of the country and have your lands confiscated.
Oh,
We
no.
arrived in the United States just in time for the American Revolution. So we got off the boat and were handed muskets, basically.
Yeah. Well,
So
Detlef,
anyway,
Yes.
that's my
I'm
connection
from
with
Hamburg.
Brandenburg.
Yep.
and
Thank you.
thank you so much, Detlef.
Yep.
Thank you, Detlef.
Okay.
And let me go back to Michael. We've got about 20 minutes left, so I'll go back to Michael. Sir?
Yes. Michael.
There we are. So let's see. I had some other, oh darn it. Where'd my notes go?
I have them right in front of me.
Yeah, no trepidation at all with
Pardon
that one.
me. Yes.
Well,
no.
so I guess Michael Boyd was mentioning the a band gap like in a semiconductor. I suppose in a sense you could think of the vacuum breakdown voltage as a band gap in a sense, because you have electrons and holes or electrons and positrons.
Yes.
So there's that. And what was the other thing? Darn it.
Well, you can think of a band gap as on one side of the band gap, we have one set of physics operating, and then on the other side, we don't have as much physics operating. You know, like a spark forming between two charged plates. Until the spark forms, there's no plasma.
Yeah.
And the electric field just sits there, and then the spark forms, like from a cosmic ray or something. And then we get a spark, we get a plasma, and suddenly the physics has changed dramatically.
Yeah, that's more of a phase change sort of. Actually, yeah, this is getting me back to where, yeah. So if we think about that analogy with time cones that I mentioned with electrostatic particles.
Yes.
For the vacuum, because of the uncertainty principle, the virtual particles have a finite range of interaction in that electrostatic sense.
Yes.
What's interesting is if you look carefully at it, that range of interaction roughly corresponds to the weak force and the strong force. So you can think of the weak force and the strong force as phase changes in the vacuum at higher energies.
I will simply say that if you look at the references, and unfortunately I forgot to put the references on but if you just go searches for recent papers, something really remarkable happened when I was working for a company called Morningstar Applied Physics, run by the late great Paul Murad, whom we lost during the COVID epidemic. He was fighting cancer and unfortunately passed away due to COVID. But he as it turns out, the masses of the meson, the charged mesons and the charged W particles fall out of the gem theory. Quite unexpected. All I can do is refer you to an article in the JMS journal. And if you do a look on Brandenburg gem theory, it'll pop right up, and it's on my research notes, so you can download it for free.
Yeah, that would be very interesting to look at, because what I'm trying to do is represent.
I'll try and include that in the chat.
Yeah. I'm trying to develop not necessarily a new model, but a new way of looking at the existing model to demonstrate, in a sense, that the W and Z bosons are like a second order nonlinear term, and then color charge and all that is a third order nonlinear term. In a sense,
the unexpected appearance of those particles in my theory kind of confirms that point of view. That
awesome. I definitely want to look at that paper then.
That's right. It's yeah, just do a search on Brandenburg under research notes and the gem theory, and it'll have that paper which you can download.
Awesome.
For free.
Oh, and then there was one last thing. This is actually,
and also it's in the book about the gem theory that I published through a German publisher.
Cool.
And so let me tell you, it was absolutely astonishing.
Yeah, I would
find it falling out of the theory that I intended to just unify gravity and E&M. And suddenly,
well, I think that there's no way at this point to just unify one without figuring out all the other stuff, kind of. Yeah,
well,
it falls out.
Yeah, you can look on the long-range forces of nature as one limit, and then there's the short-range forces of nature, the strong and the weak.
Right.
And they can apparently all, to first approximation. I actually, well, anyway, it was quite unexpected and astonishing.
Cool. Yeah. Well, that's so. If you think of the polarizable vacuum model, where you have a variable refractive index, you have to assume that in order for an observer to see a constant speed of light, that particles themselves are affected by the refractive index of space exactly the same way the light is. Therefore, an observer would always see a constant speed of light because they're affected the same way.
Sure.
So in order to make that assumption, the easiest way to do that and with the rest of the forces and particle physics is to assume that particles are still light, they're just solitons that are stabilized by some nonlinearity.
Sure.
Yeah, and then if it's still electromagnetic in nature, therefore it'll still be affected by the same refractive indices and everything else, and it's beautiful. But yeah,
it is.
That's the idea. And I had one more comment for our previous.
You're a young man. Look at all of the great things that are being laid before you.
I know. I'm enjoying this. I'm enjoying this greatly, and I hope I can contribute something to it. So
be persistent. Be dogged.
I will. So this Friedrich Morgenthaler. Oh yeah. So this I want to reference for the previous speaker if he's still here. I don't know.
Yeah, he's still here.
Cool.
Yeah. So Riccardo, he's still there.
Ricardo. Yeah. So I found this paper by a guy named Friedrich Morgenthaler, which describes, so we were talking about refractive index changes in vacuum being non-conservative in energy. So,
right.
So there's two cases. There's the space-like boundary, like going from air to glass or vacuum to glass or whatever. And then there's a time-like boundary. And if you have a time-like boundary in material properties, the energy does indeed change to an observer. So if you go read Friedrich Morgenthaler's paper, then that would be the case there. But if by the polarizable vacuum model, we're kind of assuming that we're inside of a black hole and this refractive index change is due to some external behaviors, then those boundaries would be space-like and you would conserve energy in a sense. But if you have a time-like boundary where, like, imagine you have a, actually, yeah, a perfect example, optical parametric oscillators. So if you have a nonlinear optical crystal, you apply an external electric field, you change the refractive index, you can actually pump light like a laser that way.
Yeah.
So,
yeah.
So that's very non-conservative. You have to have that flux of energy coming in to emit the laser. But yeah.
Well, someone pays the electric bill eventually.
Exactly. Yes.
I
Point being though that when you have a time-like change in refractive index, it doesn't conserve energy, and that paper demonstrates why.
Look, I obviously don't know the paper, the specific paper that you're talking about.
I will type it in the chat.
Yeah, but okay. I'm not sure I would agree. Just because someone's written about it doesn't make it true. I mean, if that's the case, then everything I write about is absolutely accurate. So I'm not sure. I'm still not sure what you're getting at. Is there any experimental evidence to support the claims made in this paper?
Yes, optical parametric oscillators, various plasma oscillations.
No. I mean specifically in the cosmological sense. Is there anything at all?
Well, no, but I mean, if you're saying that it's a material medium with optical properties defined by vacuum, then I don't see what would be different necessarily.
No, what's different is, I'll give you the first thing that comes to mind. In whatever paper you're talking about, that does not deal with zero-point field theory, I'm guessing, and it doesn't describe how light interact or doesn't interact with the zero-point field. Am I correct in that assumption?
Well, it is classical, but well, yeah, I'd have to look at that, I guess.
If it doesn't do that, then we're not talking about the same thing. So reading that paper is valueless, is what I'm getting at.
Well, it would be interesting to try and extend it and see how it matches up.
See, the reason
it's classical electromagnetism. Oh, sorry.
Yeah, so the reason I'm pushing back on this is because what I've been able to do is derive accurately, experimentally verified the CMBR. I can actually derive that. I can derive the Hubble constant, right? So not just the cosmological Hubble constant, I also derive the astronomical Hubble constant, hence giving rise to the Hubble tension you might have heard. Using the same equation, I actually calculate exact solutions for the proton and the neutron, both experimentally verified to many significant figures. So this is why I'm pushing back, because it's an investment in time to really read and understand what someone's done. It's not a trivial thing.
Well, this is a relatively straightforward classical electromagnetism paper. It's quite easy to understand.
All right,
I could even help you out if you want.
Feel free to.
Yeah, I mean, ultimately, if your theory is right, it's got to have some relation to all this stuff. So, and yeah, it's got a lot going for it. I definitely should say it's got a lot of good predictions.
Well, yeah, push that through. I'll manage it somehow.
Cool. Yeah, I've got that in the chat. Velocity modulation, Friedrich Morgenthaler, velocity modulation of electromagnetic waves.
Yeah, right.
Cool. And that's everything. Yeah.
Okay. No, all good. All good.
Okay. Well, let me go to Mr. Thomas Falone, Dr. Thomas Falone again. Tom, go for it, sir.
Yes, Tom.
John, not to change the subject or anything, but
sure. Go ahead and change the subject.
Oops, I'm going to change the subject and somehow throw.
I'm going to talk about that at a future APEC conference. I've already agreed with Tim.
It's an amazing book, and I wondered if you, for this kind of crowd, whether you could do the appendix, which is the calculation of the fission yield on Mars, besides the discovery and how you did it. In other words, summarize the whole book in a slideshow.
No, I will be presenting on that, because we now have, let me put it this way. it is well known in the weapons community that the Martian isotopes of xenon in particular give forensic evidence for a massive nuclear explosion using what's called R process, meaning rapid. It's the same process that occurs in a supernova. And if you just have slow fission, you don't get that peak at 129, it's xenon 129. Everything is higher, of higher atomic weight. But, you know, I worked for almost 10 years at nuclear weapons labs, and the motivation for the book, as I'll discuss in my talk, is no one has ever gone through an international crisis till you've been in a nuclear weapons lab and gone through an international crisis.
Yeah, your story
And seen people who apparently were in the decision chain for nuclear weapons release, dying of stress.
Yeah.
So anyway, I'll just leave it at that. I will be addressing, basically we found from supernova data, the xenon 129 spike in supernova data simulations.
The appendix, you actually calculate the yield, which is it's physics and very interesting and very.
I will go into that when I give the talk at the next APEC conference.
That would be greatly appreciated, I think, for this, and to have it recorded, obviously, as Tim is doing.
Yes, I grew up in the shadow, as we all did, of the specter of nuclear war.
Yeah.
During the Cold War, we thought it had disappeared. Now it is, of course, back again. Nuclear weapons haven't gone anyplace.
But you got permission to actually release this data from the DoD, which I thought was very impressive too. That's what you say.
I informed the first people I informed was the Department of Defense.
That's what I heard.
And they absorbed. I briefed a member of the DIA on my findings, and he said, "We'll get back to you." And then 6 months later, I got the message, "Go ahead and publish."
I'm surprised.
Well, if it's anything that tells you something about, not only are we not alone in the universe, but the rest of the universe is just as screwed up as this planet is.
Yeah.
If that was possible.
Right.
So anyway, I will leave it at that. That's a different physics problem right now.
Thank you.
Yeah, and
Right now we're worried about getting to Mars. There. Yes.
I'm hoping to have John back on hopefully April 23rd, sir. Although, you know, we've got stuff in May as well. So
I understand.
yeah,
Whenever you can squeeze me in.
I've got notes made on that.
Of the latest data.
Yeah, no, I'm excited. I'm excited. People are kind of coming back from, you know, again, we missed a session last month. It was kind of like, you know, vacation March, I guess, but it seems like everybody's kind of back in full force. So
right.
Yeah, so it's exciting. Okay, well, so I mean, we've got just about 2 minutes left. If anybody else has a question to squeeze in really quick, and if not, let me see, Ross Small, and Ross is actually with us.
Yep.
And I think, it looks like we're just about all set. So yeah, it's 3:59. Let me do this then. I want to put this thing on gallery view, and everyone, please give Dr. John Brandenburg
Thank you
big
very
applause.
much. It's an honor to address you.
John, thank you so much. Thank you so much. GEM theory is amazing, and I know that you've done years and years and years of work. So I think I am absolutely honored that you chose to speak with it, you know, with us. So
well, thanks. The honor is mine to be invited. Thank you.
Well, and thank you again. So let me see. Next, let me see if Ross Small is ready to present yet.
Pardon me while I
oh yeah, no,
post those things to the chat room that you requested.